Hello everyone, this video is continuation part of the last video, quick sort. So now I am taking some example and we are applying partition procedure. Now we'll see how partition will be applied. Partition ALH. A is my array, so I am considering the pivot element. My pivot element is the first index, that is what AL. Now I am taking two variables. One is pointing to the first low index, the other is pointing to the high index. So we'll take example also parallelly. So this is what I am telling. This is what our low index, this is what our high index. So take some elements 20, 26, 18, 22, 25, 16, some 13. So I'm taking these elements. So these elements are not in sorted fashion. So I'm considering this 20 as my pivot element. So considering 20 as pivot element. Now 20, whichever element is less than in this sorting list, that should be before of 20. So 13, 16, 18 were in the wrong place. They should before 20, correct? So there should be a procedure which is required to get into the correct list. So that is what partitioning procedure. So I am taking I from L, J from H, right? Now I am going to take a condition while I less than J. That's what we were discussed in the previous example. Till I met J or J met I, the crossing, right? By the time it goes increase, by the time it comes and decrease, one point they'll meet, they'll cross each other. That point is what? I less than J. Till I less than J, we will be performing this. What is this? I plus plus, and while we'll compare with A of I less than equal to pivot element. When you find this condition, increase the I and do J minus minus. Now this time while A of J greater pivot. So when you are going from this end to, you are finding the greater element. So that is the mean you are increasing the index of I plus plus. You are coming from this side, you are decreasing the J minus minus, and J always will search for the smaller element from the pivot element. Now this condition, so once after you finish this both the conditions, now what it is required? If I is less than J, then swap is required. Swap A of I comma A of J is required. Now once after you finish this, now finally you swap the A of L to A of J, right? So this is what finding the perfect place of pivot element to J. You will swap these elements. Let us see that if you find this is the correct place of pivot element, what happens? Pivot will come here 20 and 18, 16, 13 may not be in the order or may be in the order, will come this side, will fall this side. And after 20, whichever elements were there, all will fall this side. And it may not be sure that left side will be sorting and right side will be sorting. No, it may not be true. But the true is what? By the time you find the perfect place of A of L comma A of J, when the moment you find J, that is the place of exchange of your pivot to J. So now when you find this pivot place, your list will be in a shape that left of pivot will be less than, right of pivot will be greater than. So this is what partition algorithm, how it works in one list of array. Now we'll see the analysis, how we'll get calculated the complexity. Let us consider the list of elements where the list is having 15. Take some example 1 to 15. So in the quicksort learning algorithm, in the previous video, we were recursively applied quicksort from 1 to j minus 1. This one is p, the starting index, and j plus 1 to q. This was we were discussed in the first video. Now 1 comma 15. So there is no j we are talking, right? The list is something like this. Once you find the j, you will not going to see what is j here, how to sort it, because it is already sorted. Your main aim is what? You have to sort this and this list. So find out the j first of all here. J is what? Let us assume that j is median of your list. Why the reason I am considering median? Now take some example that there is a sequence of numbers 4, 2, 8, 7, 6, 5. Now if you take this series of numbers, if I am saying this 8 is median of the list, then this median is what? All before these elements will be smaller to the list. And let us take this, change these elements, take out this 5. Now it seems to be right, correct? Our example will be justified. So if it is a median, before these elements it will be lesser, after this it will be greater. So my assumption is what? I am considering the pivot element in the middle position. This is my first case. I am considering the pivot in the middle position. So the middle position is what? 8. 1 plus 15 by 2, which is 8. So I should not sort again 8. So what I have to do is I should go for 1 to 7, and this is from 9 to 15. I should not take 8 as per the algorithm. So now again your median value of 1 comma 7 is what? So it will be taken 1 plus 7 by 2, which is 4. 8 by 2, which is 4. Now 1 comma 3 over here, 5 comma 7 over here. Now the same, here it will be 1 comma 1, here it will be 3 comma 3, because 2 is the median. 5 comma 7, 5 comma 5 comma 7 comma 7, median is 6. 9 comma 15, 9 comma 11, and 13 comma 15, because 12 is the median. And 9 comma 9, 10 is the median. 11 comma 11, 13 comma 13, 15 comma 15. Now what is the height of this tree? It seems that recursive tree of a quicksort. Now partitioning algorithm is comparing the elements and exchanging them for n times. 1 to 15 n times. 1 to with less of one element, right? It is what? N. Again here you need n comparisons, of course with loss of single element, but you are doing for n times, and this is what your single element, leave that. Now so if you see this, the list is divided, here it is the n, and here it got n by 2, and here it again got n by 2 by 2, which is n by 4, and if you see that it is again 1 by 2 square, 2 cube, 2 power 4, 2 power 5. So finally you can write this, right? What you can write? N by 2 power k is equal to 1. That means n is equal to 2 power k. That means if you apply logarithm, log n base 2. So how many levels are there? Log n levels. In each level, I am assuming that partition algorithm compares n times. So the time complexity of quicksort is big O n log n. And this is what the best case partitioning in the middle. That's what we were taking the pivot element in the middle. So the time complexity of quicksort is what? Big O of n log n. And even we can calculate what is the complexity of a worst case. Let's take that worst case complexity. Now for this time I am not going to take middle element as pivot element. For the previous case we were taken middle element as pivot. Now I am taking starting element as pivot element. And this example is what? Worst case example. So in the worst case, if you see that the entire list is in sorted manner, correct? Entire list is in sorted manner with one comparison. Now, though it is in sorted manner, again we have to sort it, right? Let us see. Now this I am assuming as my pivot element. So as far as pivot element is concerned, partitioning will be helpful to us that to find the correct place of this pivot element such that all the left should be less, all the right should be greater. Now condition apply, I mean here in the example all these are greater elements. And now your division of the list, sub problem division is 1 to 7 elements, 1 2 3 4 5 6 7 elements. Now so we are leaving the first element, right, as it is already sorted. Then we will be going for 2 comma 7 and then 3 7, then 4 7, then 5 7, then 6 7, then 7 7. So here 1 comma 7 means n elements, 2 comma 7 is n minus 1, n minus 2, dash dash 1. So if you find the series of it, so the series is what? N into n plus 1 by 2. Finally it is what? Big O of n square. To the worst case complexity of a quicksort is big O of n square, order of n square. To reduce this complexity from big O of n square to big O of n log n, we will choose pivot element selectedly in middle position. Select middle element as pivot element, select random element as pivot element. So the worst case complexity of quicksort is big O of n square. The best complexity, average complexity is big O of n log n. Thank you all.